This is Co-17C, in case you weren't sure. I'm James. Welcome to class. Today is the last day of September. So, lots of things. Ooh, I should probably scooch this up a little bit. That's a little better. I'm imagine you're all aware, but just to make sure, there is some review that Professor Lewis posted from 17A and 17B. We should probably talk about a little bit of that. So let's go ahead and look at, specifically I was asked to talk about optimization. So we'll look at a problem similar to the one that's on there, but I kind of want to leave that one for you all to do on your own. So let's say we have the following situation. Let's make sure I write this problem in a somewhat decent way. So suppose we have a box with a square base and no top, and we want it to hold 32 cubic feet of volume. What dimensions can the box have so here's how we usually phrase this, so that we minimize the amount of material used. What we really mean is so that we minimize the surface area of the box. So when we talk about the material you're using to make some like surfacey, right, some three-dimensional thing that's like the outer surface of a container, we usually call that the amount of material, but we really mean the surface area. So that the surface area is minimized. Thank you. Appreciate it. If you didn't get this now, you can get it later. So typically for an optimization problem like this, you would want to draw a picture if you weren't given one. We know we have a box, it has a square base and no top. So it's going to look something like this. There's my box. And since I don't know any of the dimensions of the box, that's what I'm actually trying to find, we typically label those using variables. We knew that the base is supposed to be square, so this length and this depth, we should use the same variable because they should be the same value. Conversely, the height is not the same necessarily as the base or the depth. So we're going to call that a different variable. Let's call it y. After we've drawn a picture, we'll think, and you can make this picture different. Right? You could like draw on the parts we can't see if you like. Poorly. Right, there's the behind the scenes part of the box there. We want to set up essentially two equations. We want an equation for the thing that we're trying to optimize. In this case, we're trying to minimize the surface area. And we'll start there actually. So we want to minimize the surface area. So the surface area equation is going to be, let's see, I have the bottom of the box, which is x times x. I have the front face, which is x times y. I have the back face, which is also x times y. I have the left side face, which is also x times y. The right side face, which also is x times y. So we have four faces that all have an area of x times y. So we have a 4 times x times y. If the box wasn't open, if it was closed, we'd have a 2x squared plus a 4xy. And the thing we're trying to optimize is just the thing we have, right? It shouldn't ever be equal to a number because we don't know what value it has yet, right? We're trying to make it as small as possible. The reason I point this out is because a lot of times I see people make the mistake of setting this equal to 32, even though that's not the right thing. The other thing we have, oh, I should point out. So, and here's we're going to make some connections to what we're going to be doing in the future. So from 17a, this thing that we're trying to minimize is a function of two variables. We can't minimize that yet because to minimize it, we have to make it a function of one variable, take the derivative, set it equal to 0, find the critical values, et cetera, et cetera, et cetera. In a similar way, in your near future, we're going to be doing that same thing, except we're going to be doing it for a function of two variables. So instead of having a function of one variable, we're going to have a function of two variables, kind of like we have here, taking its partial derivatives, setting them each equal to 0 to find the critical point. or points for that function. So similar-ish kind of idea, but a little bit different in execution, which we'll definitely get to later. So that's why we're talking about this now, is because you're going to be doing something very much like it in the near future. The other thing we need here is we need the constraint. This will also probably be true because often for your future problems, you're going to start off with a function of 3 variables and need to eliminate one of those variables, so it's really only a function of 2 variables, so then we can use the similar process. Here, our constraint is we want the volume, we want the box to hold 32 cubic feet. So our volume, which has an equation of x times y, or base times depth times height, which is x squared times y, that is equal to a number, it's 32. So your constraint should typically be equal to some number or some given constant. They might do something annoying, like say it's c, which always feels like a pain, but that's a valid choice. But here, our volume is 32. So now we're going to use this constraint equation to isolate one of the variables. You usually want to pick the easier choice. Here, I would pick isolating y, say that y is equal to 32 divided by x squared, and then substitute that back into the thing we want to optimize. So here, we're going to say that our surface area equation is now given by x squared plus 4 times x times 32 divided by x squared. And at this point, it's probably worthwhile to write it actually as a function. Let me switch this up just a little bit more. So we can actually say that our function that we're trying to minimize, f of x, is equal to x squared plus, let's actually simplify this. 4 times 32 is 128. And x divided by x squared is dividing by x or multiplying by x to the negative 1. And I do want to write it as that because that's going to make it easier to differentiate. So then, to find the critical points, we're going to take the first derivative. We're going to say it's, let's see, 2x minus 128 times x to the negative second, and set that equal to 0. And I probably need a little bit more room here. Nope, that's interesting. So let's see. We're trying to solve 2x minus 120. Gosh, I keep wanting to write the 8 first. 128x to the negative second equal to 0. There's a couple ways to do this. I would probably do it the following way. Think of it, how would I really do this? Yeah, I'd probably write it as 2x equal to positive 128 divided by x squared, multiply both sides by x squared to get 2x cubed equal to 128, divide both sides by 2 to get x cubed equal to 64, and then take the cube root of both sides and get x equal to 4. Something that we usually had to do for this process was to verify that our critical point actually gave us the kind of thing we were looking for. So what I'm saying here, what I'm hoping here, is that x being 4, meaning that side length having a length of 4 feet, is going to minimize the amount of material we're using or the amount of surface area that we'll have. But just finding the critical point doesn't guarantee it's a minimum, right? It could be a maximum. Usually it's going to be the thing you're looking for, but we still kind of need to check. And specifically, in the future process we're going to use, the way we check is almost always by using the second derivative test or a variation of the second derivative test for functions of 2 variables. So we're going to check, does x equal to 4 minimize the function f of x equal to x squared plus 128 times x to the negative first? So the way we're going to check this is by using the second derivative test. So our first derivative was 2x minus 128 x to the negative second. And our second derivative is 2 plus 128 times 2, which is 256, times x to the negative third. Or as I'm going to write 2 plus 256 divided by x cubed. So what does the first derivative tell us about a function? Well, if the first derivative is positive, we know the function is what? Oh, good question. First derivative is positive, the slope is positive, meaning the function is getting larger. It's an increasing function. So, quick aside here, if the first derivative is positive, then we know that the function itself is increasing. And similarly, if the first derivative is negative, then we know that the function is decreasing. For second derivatives, there is a similar thing we can say. If the second derivative is positive, what do we know about the function f? Sorry, you can't see that. Also, by the way, if I'm writing things you can't see, just let me know. Hey, James, you can't see what the rest. What does it mean for the second derivative to be positive? What kind of shape does the function have? Any guesses? Yeah, we would say it's concave up. So if the second derivative is positive, we are concave up. I always like to say this like a cup. And if the second derivative is negative, then we are concave down like a frown. Meaning it opens downwards or it opens upwards. So here's the deal. If you have a critical point where the derivative is equal to 0, if the function happens to be concave up there, then you know you have a minimum. If the function happens to be concave down at your critical point, then you know you have a maximum. And here's the bad thing about the second derivative test. If your second derivative happens to equal 0, you don't know anything. You don't know if it's a maximum or a minimum or neither. Because literally any of those things can happen if your second derivative is negative. We're not going to worry about that though. So looking back here, if we look at our second derivative and we take our critical point and plug that critical point into the second derivative, we're going to see that f double prime of 4 is equal to 2 plus 256 divided by 4 cubed. I don't care about the value, I just care about the sign. This is certainly going to be positive, which means means our function f of x is concave up at x equal to 4, which means we do indeed have a minimum at x equal to 4. So we have a minimum at x equal to 4 feet. The reason I'm going into such great detail here is because this is exactly what you do when you're testing to see if a function of two variables has a maximum or a minimum at a critical point. You test this other thing we haven't talked about yet, and if it ends up being positive, then you have to go and check, okay, is my second derivative positive or negative? If my second derivative is positive, that means concave up, you have a minimum. Second derivative is negative, it means concave down, you have a maximum. So that's how we check whether we have a max or a min for functions of two variables. For this problem, we're not quite done because I think my question was to find the dimensions. I might not even get my question. So, I did what dimensions can the box have so the surface is minimized? We found the length of x, but we still need to find the length of y. So typically, when you're going back and finding the other variable, you want to go back and look through your work and see where you wrote like y equals something. So I look back here, I can see right there, I have y equal to 32 divided by x squared. So plugging in x equal to 4, we get y equal to 32 divided by 4 squared, which is 32 over 16, which is 2 feet. So there's your y value, there's your x value. Those are the dimensions of this box that minimize its volume, minimize its surface area with a set volume. The problem that he's given on his handout here is similar, but it's kind of the opposite way. So he's giving you a set surface area and asking you to find the dimensions that maximize the volume, I believe. Yeah. So similar-ish process, except in that process, you'll have the surface area equation equal to 6, and your surface area equation will have a 2x squared because the box is not an open box, right? Yeah, it is a closed box because you're trying to wrap a present in it. You need all sides to be closed. And then your volume x squared times y or x squared times h is what you'll be trying to maximize. This one, I feel like the other version of this is a little bit less nice, actually. because when you isolate a variable in the surface area equation, you're going to isolate y, and you're going to get like 4xy equal to whatever number minus x squared, and then dividing by 4x. So it's a little bit grosser, but still very, very doable. Let's go. Yeah, we might as well look at the other version. Let's look at the other side of this coin. So, similar question. I'm still going to keep it an open top box just because I think I don't want to exactly do the problem that's on your handout because you should practice it on your own. It's good to practice, right? I'll say this maybe a lot. You learn math by doing math. I know it seems kind of dumb, but it's true, right? I mean, you can see me do a lot of math and maybe get an idea of how things work, but really the way you're going to learn it is by actually doing problems on your own and maybe getting people to check your work at some point. But like, you have to do it to learn it. I'll say it a lot. You have to do it to learn it. You have to do it a lot. Okay, so similar question. Now we want to have still a box with a square base and open top. But this time we have a set value for the surface area. We want the surface area to be, what do I want the surface area to be here? 1 second. 36 plus 108 square feet. Hopefully that'll come out nice. But if it doesn't, sometimes the numbers don't come out nice, and that's also something we get to deal with. So we can draw the same picture. We probably don't really need to draw the same picture because it's literally the same picture. There's our open top box with x, and y as the dimensions. So now we want to maximize the volume, which is x squared multiplied by y. And we want to have or we don't want, we have a constraint, which is the surface area value. So our surface area equation is the bottom side, x squared, plus the 4 sides, x times y 4 times. And we want that surface area to be equal to 108. I'm just going to emphasize this because I feel like people miss it a lot. Your constraint equation should be an equation, meaning it should equal some number. Whereas the thing we're trying to optimize is just some expression, right? X squared times y. It's not equal to a number. We're trying to find the number it ends up being. So let's go ahead and do the same. So looking here, right, isolating either one of these variables, you could choose to isolate x. You should not. It is the wrongest choice you can make here. You always want to make the choice that is easier to isolate. So here we definitely want to isolate y. Isolating x would actually require the use of the quadratic formula, which really seems like not a great idea. So we're going to isolate y. We're going to have 4xy equal to 108 minus x squared, and then y is equal to 108 minus x squared divided by 4x. And I'm not going to simplify this any further because I can see that I'm going to be multiplying this by x squared, and I'm just going to cancel one of those x's. So I don't want to do more work than I really need to at this point. So now we want to maximize our volume equation is going to be x squared times y, which is going to be 108 minus x squared divided by 4x. I can cancel one of the x's at the bottom with one of the x's on the top. I would probably choose to rewrite this as, instead of dividing by 4, let's say the 1/4 is out in front. And I will distribute the x to each of the top terms and get 108x minus x cubed. That's probably the nicest way to write this equation so that it's easy to find the critical values of it, or easy to differentiate. At this point, also, you don't have to, but it's pretty common practice to write this as v of x or f of x or something so that you can write it, so that you're really emphasizing the fact that you have a function of a single variable x or whatever variable you happen to have. So here I should really say this is my v of x is equal to that. My first derivative here, why don't you all take the first derivative while I take a sip of water? If you've taken it, go ahead and set it equal to 0 and find those critical values. There's my derivative. It's 1/4 times the parentheses 108 minus 3x squared. Setting that equal to 0, you can multiply both sides by 4. We have essentially 108 minus 3x squared equal to 0, or 108 equal to 3x squared, or 108 divided by 3 is equal to x squared. 108 divided by 3 is 36. So now, what are the solutions to this equation? If x squared is equal to 36, x could either be, right, plus or minus 6. Now, the question we have to ask ourselves is, do both of those answers actually make sense? And the answer is obviously no, right? We can't have a box with a negative length. So when you're solving problems like this that involve sort of like real world examples where you have things that are measuring a physical distance or a physical area, your answer should be non-negative. So here, even though this equation has two solutions, we only want the solution that makes sense. So x equals 6. In the same sort of way we did last time, we're going to check to see if this critical point gives us a maximum or minimum using the second derivative test. So second derivative test, as its name would imply, we need the second derivative of our function. So this is important. When you're doing this part, you can't look like it, all this like algebraic simplification I've done. You have to go back to where you have like the derivative is equal to whatever it's equal to, and then differentiate that. So our second derivative here, the 1/4 is just going to hang out. And the derivative of 108 minus 3x squared is 0 minus 6x, which is equal to negative 6x over 4 or negative 3x over 2. And certainly, if I plug in a positive value of x, in this case 6, v double prime of 6 is going to be negative 3 times 6 over 2. I don't really care that it's equal to negative 9. I just care that it's negative. And here's where it always gets twisted. Our second derivative is negative. So do we have a maximum or a minimum? Right. I really, really, really encourage you to think about the fact that the second derivative being negative means it's concave down. I always like to say, okay, this means concave down, like a frown, means we have a maximum. So cool. We showed that x equal to 6 maximizes the volume function. We still should find the other dimension. So if x is 6, let's see, somewhere right here is where it says what y is equal to. So then we're going to get y equal to 108 minus 6 squared over 4 times 6, which is 108 minus 36 is 72 divided by 24, which is 3. So x is 6 feet, y is 3 feet. And those dimensions maximize the volume of this box with a fixed surface area. For problems like this, where you have an open top box, you almost always get that the height is half the width, or the height is half either the base or the depth. Whether you're given the volume and minimizing the surface area, or given the surface area and maximizing the volume, it almost always kind of works out that way. Say it one more time. Like these two equations up here. So for the volume equation, right? Because again, the problem said we want to, I might not have written it down, but we want a box with a square base and over the top, but this time we want the surface area to be 108 feet squared. And I should have said or written, we want to maximize the volume of the box. Apologies for missing that key detail. So yeah, the volume equation we're getting for any sort of rectangular box shape, it's just base times depth times height. And then the surface area for this open top box, which has 5 sides, it's the bottom side here, which is an area of x times x. And then the front face here has an area of x times y. The side face has an area of x times y. So does the back face, so does the left face here. So we have x times y 4 times. That's our regular surface area. Uh-huh. Exactly. Right, because we have another x squared on top. So soonish, towards the end of this first chapter, chapter 9, I think, we do talk about optimization for functions of 2 variables. So, and it'll be a very similar process. You'll have a function of usually x and y. You'll take something we haven't talked about yet. We'll take each of the partial derivatives with respect to x and with respect to y. We'll set each of them equal to 0 and find the critical points that way. And then we'll test the critical points in a similar but not fully defined yet way. But it's pretty much the same process. It's just kind of and actually you can say that for a lot of this class. Like a lot of the things we learned, it's pretty much the same way we did in 17A, just with like an added variable and maybe a slight extra thing. But it's a lot of the same stuff we saw before. I should ask you all, is there anything else from this, what's it called? This, I forget what it's, the 17A review problems that Dr. Lewis posted that you have questions or thoughts about? I'm looking at it right now. That's worthwhile. Sure. So I think all of you should look, and he posted it for a reason, right? Like this is definitely stuff you should be aware of. Functions, yeah. Yeah. Number 5. Estimating the derivative of a function. Okay, cool. Yeah. So let's look at, sure. I like questions like this. So I'm gonna give you a different one though. Let's keep these in order here. One second, I'm trying to scooch this down just a little bit here. Very tight quarters up here. There we go, it's a little better. Okay. So estimating the derivative of a function from its graph. I'm going to kind of give you a classic example. So let's say our function, obviously when I do this, much like your teacher has set up, it's really useful to try to draw your graph of your derivative directly below the graph of the function you've been given because it helps kind of line things up. So here's our original graph of f of x. Let's see here. Let's see what yeah, let's do that. Let me think for one moment here. Yeah, that looks good in my mind. Okay. Let's try this. Sure. So here's my graph of my function now, and so this is my f of x. We want to try and graph the derivative. A couple things I would point out. The places where you have critical points or relative extrema, like right here we have a horizontal tangent line. Right here we have a horizontal tangent line. Those are probably the places I would almost always start off with because we know that at those spots, the derivative of my function is equal to 0. So right here, we get a value of 0. And I was aiming for the origin there, but I kind of missed. So we'll live with it. So those are places where the graph is equal to 0. Now, let's look at this leftmost portion here before this first intercept for the first derivative. Over here to the left, what's my original function doing? Is it increasing or decreasing? definitely increasing, right? As you go from left to right, the y values are getting larger and larger and larger. So since over here the function is increasing, well, we just talked about how if the function is increasing, that's equivalent to the first derivative being positive. Similarly, if the function is decreasing, the first derivative should be negative. So everywhere left of here, the function should be increasing, meaning it's going to start off negative. Sorry, I'm trying. My brain said to go the right way. We are increasing, right? So I'm totally wrong. I said the wrongest thing ever. I shouldn't start off. I'm not trying to draw something that's increasing. This is increasing. My derivative should be positive above the horizontal axis. So we should start, and I'll say way, way, way over here left, my slope is very steep, so my derivative is very positive. Closer to the critical point there, my slope is still positive, but less steep, so it's going to be less positive. So we're going to do something like this. We're going to start positive, and then we're going to come at this like that. Now, between this point and that point, my function is decreasing, which means my slope, my derivative should be negative. But when I get back to here, my slope should be 0 once again. So from here to here, I have to go negative and then come back to that point there. So it's going to be something kind of like this. If you want to get a little bit more detailed, I'll point out that right about here is where I would say it looks like the slope of the tangent line is as steep as possible in the negative way. So it's kind of like a minimum for my first derivative, right? My derivative is as negative as possible. And then after that, it's less negative 0. So that corresponds to that point right there. Another way to say this is we've reached a point of inflection, right? Left of this point, your function is concave down. Right of this point, your function is concave up. And so this point here is where you go from having a first derivative that is decreasing to a first derivative that is increasing. After this point, we can see that the function is increasing, so the derivative is slightly positive, more positive, more positive, more positive. So we're going to keep getting larger and larger and larger. Certainly, when I drew this original function, I was drawing something that I imagined as a cubic function, like x cubed shifted a little bit, and its derivative should look something like x squared, which it kind of does. But we didn't need to know that to be able to draw from the get-go. I think there was something else I wanted to say here. Oh, I know what I was going to say. So another interesting fact about concavity, I think, is that when a function is concave down, any tangent line you draw should live above the function. If a function is concave up, any tangent line you draw should be below the function. And at the point of inflection, the tangent line crosses the function because on one side it's above and on one side it's below. So that's kind of neat. So right here at the point of inflection, we go through the function like that. Just kind of neat. I feel like there was something else I wanted to say here. Yeah, I know what it is. So just to say a bit more about concavity, because it is actually an important concept in this class. I mean, it's always important, but let's just point out here that this function that I've drawn just visually is always concave up. But here's what I want you to see. So for this function over here, this original function, which is concave up over here, I'll note that f being concave up, wow, can I use the right letters? F is concave up is equivalent to, well, if we look down here, it's equivalent to the first derivative. The first derivative of what? Well, I won't say it's always positive, right? Because it's actually, sorry, it's concave up from here onwards, and that corresponds to starting right here. So the first derivative doesn't necessarily have to be positive, but the first derivative is definitely increasing, right? It started off for the concave up part as negative and got less negative and then zero and then positive and more positive. So a function being concave up is equivalent to the first derivative being increasing. And then we know if a function's increasing, its derivative should be what? Right. So the derivative of the first derivative is positive. Oh yeah, we kind of said that already, right? If the function is concave up, the second derivative is positive. But there's another meaning as well. If the function is concave up, the first derivative is increasing and the second derivative is positive. And then if it's concave down, the first derivative is decreasing, the second derivative is negative. Kind of cool. So then we could totally look at the example that was given on the handout. Geez, papers. So for example, he gives, interesting, sure. So he gives this example, which I'll try my best to draw. Yeah, this example, interesting. This example should look maybe familiar, especially if you've taken a stats class ever. So here's the function that he has drawn for you, or displayed for you. And it goes up to almost 1. And if we were to try and draw the derivative, well, it looks like we have, well, I would say one thing, first of all, we have some symmetry here, right? This graph has nice symmetry. It's reflective about the y-axis. Once we've drawn the left side of it, we should be able to draw the right side of it just by kind of doing a mirror image sort of thing. So it's always worthwhile to kind of abuse any symmetrical properties you have to your advantage. So if I was going to try and draw the derivative of this, it's always good to try and line things up. So first and foremost, I'm always looking for any places where the derivative is going to be 0 because it's just an easy place to start. And I can see definitely right there in the middle, my derivative is certainly 0. We are maximizing out there. So we're going to get point right there. Okay. To make sure we think about this the right way. In fact, I'm going to just write some words here. So over here, we can see that the function is increasing. So over here, the function, I should not say the function, I should say the derivative should be positive. All right, so I want you on your own to see if you can identify where on this original function the first derivative looks like it's the most positive. Try and just plot that point on that first function. Or if you haven't drawn it, think about where it might live. It's not going to be exact. Let's see. I'm thinking it's probably right about like here-ish. Right there is where it looks like if I drew a tangent line, it would be the steepest it could be. Right? Because if I move a little further to the right, my tangent line starts to kind of get less steep. And if I move further to the left, same sort of deal. I might not have plotted it perfectly, but it's somewhere about there. So that's where my first derivative is going to have a maximum. So anywhere to the left, like over here, my first derivative is very, very small because my tangent lines are almost flat. They're not exactly flat, but they're almost flat. Here, a little less flat. Here, a little less flat. So, right, we've got some steepness here. So it looks to me like, and again, I'm just kind of eyeballing this. We're going to have something that kind of maximizes there. So it's going to look something like this. But then my first derivative stops getting bigger and starts flattening out. So my first derivative gets closer and closer to being 0. And again, my drawing here is probably not great. Yeah, I could have made that look a little bit nicer. Oh well. Here's the good part though. The symmetry here means we have symmetry down here. Now, it's not the same kind of symmetry though. It's not going to be reflectively symmetry like this. It's going to be rotationally symmetric because, and here's kind of a fun fact, if your function is an even function, its derivative is an odd function. Here's a very easy example. F of x equals x cubed is an odd function. It's kind of like your primo example of an odd function. What's the derivative of x cubed? Right. A very good example of an even function. So whenever you take a derivative of a function that's even or odd, you get a function that's odd or even, meaning it switches from odd to even to odd. It's kind of neat. So here, we're going to get this shape, but it's going to be kind of like rotated down to this part down here. So it's going to go like this. And it should look symmetrical. I did not do a great job of drawing it. But the idea is this part here, this left side does not look great. These two sides should look like if you rotated this whole thing 180 degrees, it should look exactly the same as it already did. But we'll cut in the break over here. So over here, our first derivative is negative. Just like the graph would imply, right? The function is decreasing. The derivative is negative. So that's really, I would say, most of the gist of being able to draw a derivative from the original graph is recognizing if the function is either increasing or decreasing, your new derivative function should be correspondingly positive or negative, where the original function was increasing or decreasing. There's someone on the Zoom who I missed earlier. Welcome, Daniel. All right. Let's see here. What else? I hadn't really looked at this hand either. Oh, that one's kind of gross. The reason this is kind of a useful skill is we are going to be talking about functions of two variables, and we're going to be talking about how their derivatives look. So, and the kind of thing that's interesting about functions of two variables that you don't have for functions of one variable is for function of one variable, the derivative is kind of one directional, meaning we are asking how are these functions changing as we move from left to right? It's always from left to right, right? Whenever it's a function of one variable in two dimensions, you're saying, cool, as you move from left to right, is your function getting bigger or smaller? Great, that means your derivative is positive or negative. But when you have a function of two variables, like it was kind of like a surface in three dimensions, you can say, cool, well, if we're at this point, what's the derivative if you move in that direction or that direction or that direction? You can move in literally any direction of an infinite number of choices. And so we end up having something that's called the directional derivative. And it's really important to be like, okay, cool. Well, if I'm on like, I wish I had, sure. Here's, no, that's not great. I was hopeful. Like if I'm on this surface here, right, and I'm standing right here, like depending on which way I move, I might be going down the side or up the side, depending on which way I'm facing. So your directional derivative depends on what direction you're moving in. Just like if you've ever gone on a hike, right, you can be on the side of a mountain and you could either make it as hard as possible by going straight up. Your directional derivative would be very, very positive because the slope is very, very positive. Or you can go straight down, probably not the best choice. You might end up sliding down. Or you can do what's normal and follow like the path that goes typically around the mountain where your slope is not super steep. Right? So there's lots of different choices you have on the side of a surface about how steep your direction of travel is. All right. What else is on this handout here? Not a whole lot. I mean, there's some other stuff, but that's not so important. I should ask, what did you guys do in class yesterday? You talking more about like level curves, functions of two variables, trying to see what these look like, excuse me, graphically? Okay, I feel like we should probably dedicate a little bit more time to that. Yeah, a little bit more time to that. So let's look at one or two more examples and talk about how we try to kind of identify what things look like. So yeah, this is where my drawing skills will come into heavy use. So let's look at some more functions of two variables. More on drawing functions of two variables and their level curves. And to be very frank, you should try to draw them as little as possible, in my opinion. You all have some very, very powerful graphing tools available to you. I'm specifically thinking of Desmos 3D. You should use that to your fullest capability. It is super useful and it really can help you visualize what is happening. It's also good to be able to draw them, especially if you're asked to draw things on an exam or on a homework assignment. But realistically, you want to get a good idea of what these pictures look like. So let's look at, yeah, sure, we'll look at this one first. Let's say we have our function f of xy equal to 9x squared plus 4y squared. And we're going to try and graph this thing, or at least see what this graph looks like. And it's kind of gross. It's not my favorite, but we should definitely do a couple things like look at the traces. It's a reminder of what the traces are. The traces are what's happening in each of the three coordinate planes. So the xy plane is not very exciting in this case. Here's what I mean. In the xy plane, what do we set equal to 0? And let me ask you a different question. Yeah. But so just to remind everybody how I'm getting there, if I was trying to find in 2 dimensions the y-intercept, what would I be setting equal to 0? Right. So the thing you're trying to find the intercept for, you're setting the missing thing equal to 0. So if we're trying to figure out what's going on in the xy plane, where you're flat on the ground, you haven't gone up, you haven't gone down. So your z value is 0. So if we set z equal to 0, which is another name for the function, we're going to get 0 equal to 9x squared plus 4y squared. And the reason I say this isn't very interesting is because there's only one solution to this equation. X and y both have to be 0. So not a lot going on in the xy plane. But in the other two planes, in the xz plane, if we set y equal to 0, we end up getting z equal to 9x squared, which looks like a parabola. A pretty steep parabola, right? Because if x is 1, z is going to be 9. So it's a very kind of steep parabola. Whenever you're graphing traces, the z-axis is the vertical axis, and either x or y is the horizontal one if you're in the xz or the x or the yz plane. Similarly, in the yz plane, if we set x equal to 0, we end up getting z equal to 4y squared, which isn't quite as steep, but still giving us a similar graph. I'll draw it a little less steep. And then before we go on and try to just put it all together, I do think it's worthwhile to find some level curves. So here's what we don't want to do. We don't want to, I should back up a second. Before we talk about the level curves, you should talk about the domain and the range. So looking at this function, let's write the domain up here, sorry. So when we talk about domain, even though it's a function of two variables, we're still thinking back to our 17a kind of restrictions. So I'm looking for a square root, a logarithm, or a division by 0. I see none of those things here, meaning my domain is, well, be careful. Let's just, for a second, our domain is everything that's possible. But here, our domain is not on the number line. Our domain is on the number plane, the xy plane. It's every point x comma y in the xy plane. So our domain is, unfortunately, for functions of two variables, always annoying to write. Our domain here, the easiest way to write it is the set of all points x comma y such that x and y are both real. Or you could write it's the entire two-dimensional plane. But it is notably incorrect to say it's all real numbers because we're not talking about numbers, we're talking about points, which are a pair of numbers, which is annoying. On the other hand, the range is like how it used to be in 17a. It's still going to be just some interval of values because the domain is all the things that are possible in the xy plane. The range is all the possible z values you get in the third dimension. So if we look at our original function here, well, looking at this function, I can see I can definitely get a small value of 0 by setting x and y equal to 0, and we can't get anything negative out. We can certainly get any positive number that you wanted. So it looks like our range here, not our domain, is going to be the interval from 0 to infinity. And yes, this is typical for functions in two variables. Your domain is always some region in the xy plane. Sometimes it's all of it. Your your range is some interval on the z-axis. All right. The last thing we're going to do before we graph this thing is we're going to find some level curves. And here's what we did last time. Instead of picking a bunch of values that are in the range like we did last time, we're just going to say we're going to set this equal to something like c. C is the usual choice. So we're going to set our function 9x squared plus 4y squared equal to c. And how do I want to do this? Oh, that's annoying. Yeah, it's real annoying. I picked an annoying example, kind of on purpose. So this kind of looks like it might be the equation of what kind of thing? Like, yeah, you're not wrong. It has definitely circle vibes, but it's not a circle. The reason it's not exactly a circle is because the coefficient of x squared and the coefficient of y squared are different, which means it's going to be longer in one direction than the other direction, so it's going to be an oval instead of a circle. So we know this is an oval. Now the problem is not being a circle means you can't be like it's an oval with this radius because an oval doesn't have a set radius, right? It has different. So probably here I probably did the wrong thing. I probably should have just picked numbers and gone about finding my level curve. So let's go ahead and pick some numbers. Really not my drawing all these graphs is never my favorite part. But we can do it. So let's pick something like c equal to 1. Yeah, 1's annoying, but it's worthwhile. We'll do 1 and then we'll talk about some better choices. So if we have 9x squared plus 4y squared equal to 1. Okay, here's how you should graph an oval, also known as an ellipse. You find the intercepts. So you find two x-intercepts, two y-intercepts, and then try to draw your best oval. I'm going to try and make this look somewhat kind of decent. So if I set x equal to 0, I'm going to get y equal to plus or minus 1/2. If I set y equal to 0, I'm going to get 9x squared equal to 1, x squared equal to 1/9, x equal to plus or minus 1/3. Not starting off with great values, I feel like here. So it's going to be a very small oval. If that's 1 and that's -1 and that's 1 and that's -1, then my oval is like 1/2 in the y directions, 1/3 in the x directions. Oh, it's a tiny oval. I should really say ellipse. Ellipse is the more correct mathematical term. Okay, so that's where our height is equal to 1. So this right, c equal to 1 means that we are at an elevation of 1 above the xy plane. Okay, let's pick another choice that seems smart. I don't want to pick 2. I probably want to pick something like 4. So c is equal to 4. Let's see what we get. We have 9x squared plus 4y squared equal to 4. If we set x equal to 0, we're going to get 4y squared equal to 4, y squared equal to 1, y equal to plus or minus 1. We set y equal to 0, we're going to have 9x squared equal to 4, x squared equal to 4/9. x equal to plus or minus 2/3. So getting a little bit better. So we've got an idea what's happening now. We can see that as we go higher in elevation, our ovals get larger. Let's go really big. Let's say we go all the way up to c equal to 36. Super high. If we graph that, we're going to have, well, 9x squared plus 4y squared equal to 36. Again, I'm just finding the intercepts. If I set x equal to 0, I'm going to get 4y squared equal to 36. I'm going to get y squared equal to 9. I'm going to get y equal to plus or minus 3. Similarly, if we set y equal to 0, we're going to get 9x squared equal to 36. We're going to get x squared equal to 4. We're going to get x equal to plus or minus 2. So your job when you draw this is kind of think about how visually, here we're at a height of 36, here we're at a height of 4, here we're at a height of 1. So you can kind of imagine these layers stacked on top of each other, small oval at a height of 1, somewhat bigger oval at a height of 4, much, much bigger oval at a height of 36. There's one question left to answer before we try to draw this thing. And it's never a good question. Are these concentric ovals equally spaced apart or not? Meaning every time you go up one, you go out the same amount. And the answer is no here. How can you tell? You can literally tell by like increasing by one and seeing if either of your what's what I'm looking for? If either of your x-intercepts or your y-intercepts kind of increased by the same amount each time. So we didn't do that because it's a pain in the butt. But if you had said like c equals 2, you would have gotten some gross values for x and y, and then c equals 3. Okay, fine. So I'll just point out if c equals 2, we get, sorry, the numbers are not beautiful here. If we said x equal to 0, you don't need to write this right down. I just want to show you. You get 4y squared equal to 2, y squared equals 1/2, y equals plus or minus root 1 over 2. And if you set c equal to 3 and x equal to 0, you get 4y squared equal to 3, you get y squared equal to 3/4, you get y equal to plus or minus square root of 3/4. So going from a value of 1/2 to a value of root 1 over 2 to a value of root 3 over 4, you're not increasing by the same amount each time. So they're definitely not equally spaced apart. The difference here is typically between what's called a paraboloid and what's called a cone. So here we have an elliptical paraboloid. Putting our traces together and our level curves, making sure that we note that the y direction is the longer direction, the x direction is the shorter direction. We have, here's kind of my biggest level curve. And then we're going to say, here's my y direction parabola and parallel to the x-axis. So I'm kind of imagining here, this top level curve I've drawn, here's my c equal to, say, 36. And then way, way down here, here's like my c equal to 4. This ellipse like that. If I wanted to go even lower, I could draw the one where c is equal to 1. But that's kind of putting it all together. Every time you slice this thing in a plane parallel to the xy plane, you get an ellipse as you go further up that's wider and wider and wider. This is the equation. This is the graph of the equation. 9x squared plus 4y squared equal to 1. And it's a elliptical paraboloid. more generically, I apologize, that's one of the level curves. This is a level curve. The actual graph was f of xy equal to 9x squared plus 4y squared. This is your elliptical paraboloid. So that's the equation of this surface. What I wanted to say was more generically, if you graph something like f of xy equal to just x squared plus y squared, this is your regular, kind of like how y equals x squared is like your go-to parabola, your nice one that has a vertex at the origin. F of xy equal to x squared plus y squared is your go-to paraboloid. And it looks similar to this, but more like even Steven. It's a parabola in the y direction. It's a parabola in the x direction. And then your level curves are nice circles. Right? And you can kind of see that, oh yeah, if we let the function have a larger and larger and larger value, you're going to get circles of larger and larger radius. So here I'll just point out the level curves are circles that are unevenly spaced. You guys have web work, right? You're doing homework on web work. So one of the reasons I'm pointing this out is because oftentimes with this material, they'll like give you the equation of something and then ask you to determine what kind of level curves you have. And there'll be like a drop-down menu of your level curves are circles or lines or something else. And then they'll be like, and they are evenly spaced or not evenly spaced or pointing in different directions. So that's why why I'm spending some time talking about whether they're evenly spaced or not. So what kind of graph would have level curves that are evenly spaced? Well, here's one example that's going to be looking kind of similar, but not quite the same. F of xy equal to the square root of x squared plus y squared. Oh, I'm way off. Sorry, it just got very, how did I get so off center all of a sudden? Okay. So quick question. It's kind of a deceiving question. Does this function have any domain restrictions? I mean, it looks like it could because you got a square root in there. So let's talk about the domain for a second. For our domain here, our restriction is that whatever's on the inside has to be greater than or equal to 0. But in this particular case, the argument of your radical here, no matter what you choose for x and y, is still going to be positive, or I should say non-negative regardless. So we actually don't end up having any restrictions here because x squared plus y squared is already going to be positive for any choice of x and y. So our domain is still all possible points in the xy plane. So we could say all points in the xy plane. Or we could just say the set of all x, comma, y. The range is also essentially the same as it was last time. Our range is still going to be all non-negative numbers. So we can certainly get the function equal to 0 if we set x and y equal to 0, and you can get any other number. So I would point out, I have to think about the range in more detail, meaning how do I know I can actually get any number? What if I want this to equal 17? Well, I could pick x equal to 0 and y equal to 17. So oftentimes I'll think about like I'm trying to kind of, because sometimes the range is a more complicated question. Here I can be like, okay, well, if I just set one of them equal to 0, can I pick the other one equal to something that's going to give me what I want? And in this case, that's always true as long as we're picking something positive. If you set one of them equal to 0 and the other thing equal to the number you're trying to get, in this example, you can always get that number as long as it's a positive number or a non-negative number, I should say. So kind of good to think about if you can actually get any value you're trying to think about that's in the range. The only difference here between this example and the previous one is what our kind of level curves look like, how they're spaced. So let's look at some level curves. And in this example, unlike my previous example, I will point out that we should do the thing I said before, meaning we should just set it equal to C and try to solve it in a way that makes sense. So if we set the square root of x squared plus y squared equal to a constant, I'll remind you of something I said last Thursday, which is that when you're trying to figure out what your level curves are, you either want to isolate x squared plus y squared if you have it, or if you don't, try to isolate y. And if you can't isolate y, then try to isolate x. So you either want to write y is a function of x, or less good but still plausible, x is a function of y, or if you've got it, x squared plus y squared equal to something. So here, the only thing I have to do to deal with this is square both sides. It's like x squared plus y squared equal to c squared, which is kind of like the best possible situation because this is the graph of a circle with what radius? Right. Which also means that if you increase c by 1, you're going to increase your radius by 1. So at the height of 1, your circle has a radius 1. The height of 2, your circle has a radius 2. So every time you go up 1, you're also making your circle increase by the same amount, meaning our circles will be evenly spaced out. We can draw them. I don't think we get much value from that really. But for example, here's your level curve when c is equal to 1. You can use some different colors. Here's your level curve when c is equal to 2. I have a green pen. Here's your level curve when c is equal to 3. If you are asked to draw level curves, it's usually a good idea to label them. So this is c equal to 3, here's c equal to 2, here's c equal to 1. So here, if we try to graph this three-dimensionally, yeah. Things aren't equally spaced out. So if we go up to a height of 1, we're getting that circle of radius 1. If we go up to a height of 2, we're getting that circle of radius 2. And up to a height of 3, you're getting that circle of radius 3. And if we actually connect the dots here, it looks like not a paraboloid, but a cone. Because, and I kind of forgot to mention this, our level, our traces here are kind of weird. So just to go back for a second, our YZ trace, I don't want to talk about the XY trace because it's, again, just the point that's the origin. But the YZ trace, we're going to get Z equal to the square root of x squared. Okay, I want you to be extra careful. What's the square root of x squared? Not just x. You're very, very close. It is plus x if x is positive, and it's minus x if x is negative. Or in other words, it's the absolute value of x. Think about it this way. What's the square root of 5 squared? 5, right? Okay, I know it's a dumb question. Humor me. What's the square root of negative 5 squared? Is it 5 or is it negative 5? What's negative 5 squared? Right, negative 5 squared is positive 25, and the square root of positive 25 is positive 5. So the whole point here is that whether you're inputting a positive or a negative number, you're still outputting a positive number. That is literally the same thing as the absolute value. And look, there's your absolute value. Sorry, that's the one in the x. That's the one in the xz trace. Apologies. My xz trace, if I set x equal to 0, is going to be z equal to the square root of y squared, which is the absolute value of y. That's that graph there in the yz plane. In the xz plane, it's right about there. Like that. Yeah. So you've got these absolute value this way, absolute value this way, and you've got the cone all around it. So yeah, kind of a weird trace when you get the absolute value. That does come up. Ooh, yeah, it comes up in other weird places as well. All right. Ooh, ooh. I see. Okay, I see what happened there. Sorry. 1 second. Yeah, we should talk about that. Okay, how much time? Ooh, not a lot of time. Okay. Domain, sure. Meet answers there. So, looking towards the future, limits are on the horizon. And there's really a couple things I want to remind you of when it comes to limits. Yeah, I hit a button that did something. Sorry. There you go. So, the first thing you should remember about limits is to evaluate a limit, plug in when x is approaching. So if I have like the limit as x approaches 2 of x squared plus 3, I see no issues. I'm just going to substitute in 2 for x and get 2 squared plus 3, which is 7. So when we start seeing limits that where you have, instead of x approaching a number, you have xy approaching a point, like 2 comma 1, the first thing you should try to do is just plug in 2 for x and 1 for y, or whatever value x and y are approaching. But as you probably saw in 17a, most of the time that doesn't work, right? You often get what's called an indeterminate form. So the first thing you should always try to do, though, is plug it in. But then you might have a 0 over 0 indeterminate form. Indeterminate form. For example, something like the limit as x approaches 2 of x squared plus x minus 6 over x squared minus 4. Often in 17a, when we did this, we still end up getting something because you could usually factor out the challenging piece. This top part factors as, I should point out, first of all, if I plug in 2 for x, I get 0 divided by 0. I get 4 plus 2 minus 6, which is 0, over 4 minus 4, which is also 0. So this is a 0 over 0 type. Here we can factor the top as x plus 2 times x minus 2 times x plus 3. The bottom is x minus 2 times x plus 2. We can cancel the offending factors, and then we can plug in 2 for x and get 2 plus 3 over 2 plus 2. That'll occasionally happen for functions of two variables, but less often. So usually, I will say most of the time in this class, when you get 0 over 0, it's typically going to mean something more like the next example. So usually a 0 over 0, you should still keep an eye out for like, do you see something that might factor? But a lot of the time it's not going to work out. Let me show you kind of so for example, if we had the limit, sure, as x comma y approaches 2 comma 2 of say x squared minus y squared over x minus y, that looks bad, right? If I plug in 2 for x and 2 for y, I'm going to get 4 minus 4 over 2 minus 2, which is 0 over 0. What do we do? Normally, you would try something else, but here we are fortunate in that we can factor this, right? You can definitely factor the top as x minus y times x plus y. And the x minus y factor in the bottom will end up canceling. And then we can say limit as x comma y approaches 2 comma 2 is of x plus y is 2 plus 2. which is 4. But that's atypical in this class. Most of the time, when you have an indeterminate limit like this, where it's a 0 to 0, usually we're going to need something where the limit doesn't exist. Here's kind of an example from back in 17a where we have a piecewise function. So if our function is, say, x squared when x is less than or equal to 2, and x plus 1 when x is bigger than 2, if I ask what's the limit as x approaches 2 of f of x, well, we have to look at the limit from the left and the limit from the right and see if they're equal to each other. So here, the limit as x approaches 2 from the left of f of x is equal to the limit as x approaches 2 from the left of x squared, because that's what the function is defined to be on the left side of 2. And if you plug in 2, you get 2 squared, which is 4. On the other side, if you take the limit as x approaches 2 from the right of f of x, you get the limit as x approaches 2 from the right of x plus 1. You plug in 2, you get 3. Not the same. That means limit does not exist. The reason I'm showing you this is because this example is this idea is pervasive in functions of two variables, because not only does the limit from the left and the limit from the right have to exist, the limit from any direction you might approach your point has to exist. And you know how many directions there are approaching any one point in 2 dimensions? Infinite. There are literally infinite directions to check. So here's the problem. You have to keep trying different directions until you either have done enough that you've convinced yourself the limit exists, and then there's a whole other thing about showing the limit exists, which is a terrible pain, which we will talk about, but it's kind of gross. But much of the time, what's going to happen is you're going to pick 2 different directions that go through your point, and they're going to give you different limit values. So the limit's going to not exist a lot of the time when it's indeterminate. Let me show you what I mean. Let's look at something like this example. The limit, you have, very quickly, the limit as xy approaches 0, 0 of x squared minus y squared over x squared plus y squared. So here's the idea in a nutshell. You're going to pick a path, any path that goes through the point 0, 0. There's a lot of paths that go through 0, 0. One of the best ones to pick is the line y equal to 0. Right? The line y equal to 0, which is just the x-axis, definitely goes to the origin. So if I pick that path, this is my path, I'm left with the limit as x approaches 0. Y is no longer approaching 0, it is 0. And I'm left with x squared minus 0 squared over x squared plus 0 squared. What's the limit as x approaches 0 of x squared divided by x squared? What's x squared divided by x squared? 1. I'll point out, I will remind you, x approaching 0 means x is getting really, 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 really close to 0, but it is not equal to 0. We're just getting close. As long as x isn't 0, x squared divided by x squared is equal to 1. Right? 5 squared divided by 0.5 divided by 0.5 squared, anything divided by anything squared, as long as it's not 0 squared divided by 0 squared, you're safe. So this is always 1 as long as you're getting really, really close to 0. So this is the limit as x approaches 0 of 1, which is 1. On the flip side, if we pick a different path, say x equal to 0, then we have the limit as y approaches 0 of 0 minus y squared over 0 plus y squared. That's the limit as y approaches 0 of negative y squared over y squared, and negative y squared divided by y squared is negative 1. And that limit is negative 1. Those don't match. So this limit as x, y approaches 0, 0 of x squared minus y squared over x squared plus y squared does not exist, because you have paths in different directions giving different values. Next class, we'll pull up the graph of this on Desmos 3D and actually kind of look at how if you come along the x-axis, you get one value. If you come along the y-axis, you get a different value, and the limit can't exist there because you're approaching 2 different values at the same point. These 3D graphs can look very crazy because you've got all sorts of undefined or discontinuity at some point. All right, that's all I got for you. If you didn't get your name on the sign sheet, please do put it on there, and I will see you on Thursday.